number associated with that. That number is 6.02 times 10 to the 23rd. So that's the pressure in the gas, the volume multiplied by the gas, the temperature in Kelvin, the absolute temperature. R is the universal gas constant, which has this value, 8.314. This is the value that you use for R when the pressure is in pascals and the volume in cubic meters. So if the volume is in cubic meters and the pressure is in pascals, pascals times cubic meters has units of energy. So you use 8.314 when you have pascals and cubic meters divided by moles divided by Kelvin. Because if you solve for R over there, right, it would be PV, which is pascals times cubic meters, which together makes it a joule, divided by the number of moles divided by the temperature, the unit of temperature. On the other hand, if you use pressure in atmospheres, which is another unit of pressure, 1 atmosphere is 1.013 times 10 to the 5th pascals. So if you use the pressure in units of atmospheres and the volume in liters, then in that case, the value of R, with the converting these pascals to atmospheres and so on, the value of R is 0.0821. So atmospheres, liters per mole per Kelvin. Okay? No matter what, you have to use the temperature in Kelvin, right? N is the number of moles. So R could either be 8.314 or 0.0821. And it depends on which system of units you're using for the pressures and on the volumes. Okay, so there are just two different values for R depending on what system of units you're using for pressure and volume. The other formula here that relates the pressure, the volume, the absolute temperature of the gas, and this capital N represents the total number of units that make up the gas. They may be single atoms if it's a monatomic gas, or molecules, composed of 2 atoms if it's a diatomic gas. So this is the total number of atoms or molecules that makes up the gas, right? So if I notice that if I write down those two expressions, if I write like PV equals PV, and I use nRT on this side, and on the other side I use capital N and then Boltzmann constant times T. K over here is just another number, another constant. It is known as Boltzmann constant. It's just another number. 8.38 times 10 to the minus 23rd joules per Kelvin. So if I write down the ideal gas law like this, PV is nRT and PV is equal to nKT, notice that this cancels that. And so I get that N times R has to be equal to capital N divided by that, right? And so if I divide by N, I get the number of moles N, I get the capital letter N, which is the total number of atoms or molecules, divided by the number of moles, divided by Boltzmann constant. So we have this relationship over here. Now, the question is, what's this? Right? So, it's just the total number of atoms or molecules that makes up the gas, divided by the number of moles. What is that equal to? So that turns out to be equal to Avogadro's number. So, if you multiply, for example, 6.02 times 10 to the 23rd, and you multiply that by the Boltzmann constant, which is 1.38 times 10 to the minus 23rd, what do you get when you multiply those two constants? You should get 8.314. Right? So there are just 3 constants that are related by that expression. You don't really need to know this relationship because all of these constants are usually given, right? I mean, you don't need to use this formula to figure out the universal gas constant if you know the other two. I mean, this is a number, that's a number, that's a number, so they're all constants, and so, but I just wanted you to just realize that. And the question is, why is this capital N, the total number of atoms, let's say, that makes up the gas, divided by the number of moles, why is that equal to Avogadro's number? I don't know if that's obvious to you. Maybe it is, maybe it isn't. So let me sort of go over that. This is how I do it in my head, so that I hope it helps you get a picture. So, what if we have this volume here, okay? You know, total volume V, and we have, let's say, a monatomic gas. I just want to draw dots. I don't want to draw, like, you know, one atom next to another atom. I don't want to, I'll just consider a gas made up of single atoms. Argon, for example, is a gas made up of single atoms. And suppose this is atom number 1, and this is atom number 2, and this is number 3, and this is number 4, 5, 6, 7, and this is the 6.02 times 10 to the 23rd atom. And these atoms over here, this many atoms, 6.02 times 10 to the 23rd, let's say that they take up this space over here. And just imagine that in that volume, I have 6.02 times 10 to the 23rd atoms. And then this is atom number 1, atom number 2, atom number 3, atom number 4, pop, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, and then this is the 6.02 times 10 to the 23rd atom, right? And these atoms over here occupy this other space. How many? 1 all the way up to 6.02 times 10 to the 23rd. So this is number 1, number 2, number 3, number 4. I mean, these are not boundaries over here. I'm just, imagine that I freeze them at some instant of time. If I could just stop time, right, and they're all stop moving. And then you have all of these. And this is the 6.02 times 10 to the 23rd atom. Okay? So, what's little n for this gas? Just 3. This is 1 mole, this is 1 mole, this is 1 mole. You got 3 moles. Think of each one of these volumes over here as 1 row, 1 row, 1 row. You got 3 rows. So n is 3. Yes? I mean, if I put 12 here, 12 here, and 12 here, and I ask you how many dozens do I have? I got 3 dozen, right? Now, what's the total number of atoms in there?
8 times.
What's that?
18 times 10 to the 23rd.
So 3 times Avogadro's number, right? So it would be 3 times 6.02 times 10 to the 23rd, because I have 6.02 times 10 to the 23rd over here, 6.02 times 10 to the 23rd over there, 6.02 times 10 to the 23rd over there. So that's 6.02 times 10 to the 23rd times 3. But look, that's n, and this is Avogadro's number. So notice that big N over little n is Avogadro's number. That's what I used over here. Yes? And let's keep playing with this. So we have this relationship, right? Clearly, I don't know, by the definition, right? This is 1 mole. This is 1 mole here, and that's 1 mole over there. What if the mass, this is let's say this is just argon gas, and so I have a gas of just argon atoms. And what if, so they're all like, they all have the same mass. What if the mass of that is that, it's just lowercase m? That's the mass of each atom. So, what is the mass of a mole? What do you call the mass of a mole? The molar mass. Right? So, what is this? What's the mass of a mole? What would it be? If you know the mass of each one of them, and they all have the same mass.
M times Avogadro's number.
It's just this mass plus this mass plus this mass, So this would be just 6.02 times 10 to the 23rd times the mass of each one, because they all have the same mass. So notice that the mass of one mole is just Avogadro's number times the mass of each one. Yes? What if I ask you, what's the total mass of all of this gas? What's the total mass? Just capital M. Maybe I'll do it over here. What is the total mass?
3 times M times Avogadro's number.
So I can say it's the mass of this mole, plus the mass of this mole, plus the mass of this mole. So it's 3 times the mass of a mole. And that would just be N times the mass of a mole. By the way, how else could I write down the total mass of this gas? What if I want to write it down in terms of the mass of one of the one of the atoms? Then what? No, if I multiply that by Avogadro's number, I get the mass of a mole, not the total mass. Times what? No, 3 times this mass is just gonna give me, the mass of these 3 atoms. No, if I multiply by Avogadro's number, I get the mass of a mole.
He's saying 3 and Avogadro's number.
Huh?
3 Avogadro's number and M is what he's saying.
Oh, I'm sorry. You're saying what? 3?
Avogadro's number and the mass of an individual atom.
But what is this? That's the point of why I'm writing it slightly differently. Of course, what you did is you took this and you put it in there, right? But I don't want you to do that. I want you to think about it so that you understand it. What's this? Capital M. This is just, it's the mass of this plus the mass of that plus M plus M plus M plus M, all of them. It's the mass of all of them times the mass of each one. It's how many atoms I have times the mass of each one of them. No. If we all have the same mass in this room, imagine we all have the same mass, and we want to know the mass of all of us. All I need to do is find the mass of, the mass of one of us and multiply by how many of us there are. That's what this is, right? It's the mass of each one of them multiplied by how many atoms I have. That's the total mass. But I could also write the total mass as the mass of this row plus the mass of this row plus the mass of this row plus the mass of this row. So it would be the mass of a row, the molar mass, times how many moles I have. Right? That's this. So notice that I can write the number of moles as this divided by that, but I could also write it as the total mass divided by the mass of a mole. And all of these expressions can drive you nuts. At some point when I began to learn about this, I remember I just memorized these expressions, and a few days later I wouldn't remember them. And I wouldn't be able to come up with them. Nowadays, you ask me this expression, I think of this picture, and I can come up with those formulas. If I think of this picture. Thinking of a picture like this allows me to write those expressions right away without me having to access some, corner in my brain, where this thing was memorized. So anyway, in this step over here, you know, total number of them divided by the number of rows. I mean, suppose each row over here is a mole. So you have a mole, a mole, a mole, a mole, a mole, and a mole, right? If I wanted to know how many people I have in each mole, suppose I forgot Avogadro's number. How else could I find out how many moles I have? I'm sorry, the number of people in a mole. How would I find out how many people I have in that row, how many people I have in this row, how many people I have in this row?
Just know one of them.
I mean, I could do this 1, 2, 3 and count them, right? Suppose I want to know how many people are in each row. But I don't want to count 1, 2, 3, 4. But I knew the total number of people in the room. How could I find it?
Divided by 6.
So I take the total number of us, right? Divided by how many rows I have. That's what this is. It's the total number of people in the room divided by how many rows. How many groups, how many moles. And that'll tell me how many I have in each row, in each mole, in each group. That's what that formula means. So, you know, instead of just memorizing them, I'm suggesting that you think of a picture so that these formulas make some sense, because otherwise it's, you know, it's like, oh, you know. Anyway, it can be confusing because you have a lot of these n's, a little n and big N. And also you have the small m and the big M, and then the mass of a mole. So, you know, you have so many quantities to keep track of that I think it is just, at least for me, it's just a lot easier to think of this picture rather than just memorize these expressions. I mean, if I need these expressions, I think of this and then I get it from there, from the picture. I mean, it's easier for me to remember the picture than it is to remember the formula. The reason why I pulled this up is the following. In an ideal gas, right, the one that's described by this equation of state or this equation of state, they just, you know, this and that relate the pressure, the volume, and the temperature. One of them, you know, relates those quantities to the number of moles. The other one relates those quantities to the total number of atoms that makes up the gas. Now, the reason why I included this picture is that in the ideal gas case, when you think of the gas as being ideal, one thing that you do is that you do not take into account the fact that the molecules or the atoms take up some space. So you think of them as if they take up no space. Because in reality, I mean, if we think about it, if we shut the door and all of us are here, the volume that's available to me, the volume that I will be able to move, right, is the volume of the room minus the volume of all of you, because I can't go through you. Like, if imagine you all bunched together in the corner, then it's like I can't get in there, because that's, so the real volume that's available to me is the volume of the room minus the volume of all of you guys, right? So in the gas, when you write down this ideal gas equation of state, right, you are disregarding the fact that the molecules themselves take up some space. Right? Another thing that you disregard is the interactions between them. So it's like there's a molecule over there, another one over here, and you don't say I'm attracting you or I'm repelling you. None of that. The only thing that's taken into account is the fact that they can collide. Up until they collide, there's no interaction between them. That's another thing that you disregard when you write down an equation of state like that, the ideal gas law. In reality, the atoms and the molecules do take up some space, and they do interact at a distance, right? It may be because of the charge distribution that they have, these atoms have positive and negative charges, right, and so on. So then there is a correction that could be made to that equation of state. And I don't know if I read it over here. Oh, here it is. It's called the van der Waals equation of state. So the van der Waals equation of state is a correction to the ideal gas law where you take into account the fact that the molecules or atoms that make up the gas actually do take up some space. Notice how the volume is affected over here, right? It's still like pressure times volume equals nRT. But the volume is adjusted to take into account the fact that the atoms or molecules actually do take up some space. And the pressure is adjusted over here to take into account the fact that the atoms do interact with one another as they approach one another at a distance, right? So it's a more realistic expression. I think there is a homework problem where I ask you to, I think, there's a homework problem, or I don't know if it's an example, I don't remember, where, you're given parameters for a particular gas. This A and B are just numbers. This B here, lowercase b, lowercase a, they're parameters, if it's argon, it's some value. If it's hydrogen, it's some other value. So I think I don't remember, there's a homework problem where you are given these parameters for a particular type of gas, and then you're asked the question, okay, solve for the pressure or solve for the temperature or whatever, if it's an ideal gas law, and then you get a number. Now solve for the same quantity if you use the van der Waals equation of state, and the correction is very, very small. So usually you just use the equation of state for an ideal gas. But I just wanted to bring that up. And here is some comments to that effect. One thing that I was just thinking about it earlier today. Before I talk about this, I want to talk about something that I didn't say in the previous chapter, 17. We talked about melting, we talked about freezing, we talked about boiling, we talked about condensation. Let's see, unless that's in this chapter here. Not really. Not really. Okay, so it's something that I didn't say, and I would like to say something about before we continue in chapter 18. So it has to do with boiling and evaporation. There are differences and there are similarities.